Okay,
Park.
very good. We have to start the class at park.
Oh no.
Alright.
You said as a marker.
We
I'll
are
take that class.
looking at it. We had just gotten done with the worksheet on, what do you call it? First fundamental theorem of calculus. And we
the second.
started dibbling into the second fundamental theorem of calculus in the second half of that. Did I check everybody's worksheet off on that one?
Which one?
For just the one, or was the 5L dash 2 or something it's called?
Well, this is the one that,
Yeah,
but you checked out the first part, yeah.
the first part,
Yeah, but
yeah.
not five.
Not the second part.
But
Correct.
probably consider it.
So the second part we are looking at today. Let me see how what do we have? So 5, 6, 7, 8, 9, 10, basically. Okay. And hopefully the second fundamental theorem didn't stress anybody out too much or keep you up too late.
Yeah, well,
That was totally at your option.
for these two, I think.
You didn't have to show your work.
No, yeah.
All right. Oh,
Well, one he did in class with us, the other one did side by side.
correct. Yeah, I was working through. See what we've got here. Got it. So, I have a red writing utensil at the ready. Let's go through some answers. Number 5. It's an S. It's a bunch of cube roots. They simplified it. They, if you had something to the 4/3 power, that's okay. But they boiled it down to cube roots, so just be prepared. It's a big fraction. The top is 30 times the cube root of 10 minus 15 times the cube root of 5 all over 2. If anybody tries a decimal, it's roughly 19.492. I'll know what's looking at that. I'm thinking if anybody had, was it 30 times, oh wait a minute, hold on a second. Did anybody have 3 times 10 to the 4/3 power?
Wait, say that again?
I think it's 3 times 10 to the 4/3 power, minus 3 times 5 to the 4/3 power over 2.
That's 6.
Or if you had 3 in
times
front.
10 to the
Well,
fourth
so I
is
had
five.
similar to that,
Okay.
yeah.
I
But I
s-
didn't simplify all that. Like,
Yeah,
Oh, you put partial?
I
and then I
sim-
got really scared and then I was just kind of like, I don't know what to do.
I simplified like the answer, so I got
in a dark alley and I was scared. Go ahead.
I simplified the answer. I got 15 instead of 30 because I divided each side and split it up.
Oh,
Or just did that.
okay.
Yeah, might as well just.
Well, I can work that on the board if you like. I think you got it right, but we'll do that anyway. Number 6, the answer is 0.
That's right.
0?
Oh, boy. Oh.
It is.
Oh my word! What?
Wait, number 6 is 0?
It
Yeah.
does. The 2 parts cancel.
Wait, number
Yeah.
6, right?
Number 6.
Number 6, affirmative.
Number 6. Number 6.
Number 7, the answer should be negative 1 over x cubed. Shocker. The next one should, number 8 should be 3 over x cubed. Number 9 should be negative 5 over x plus 2 in parentheses cubed. And number 10 should be negative x cubed plus 4x squared minus 3. Any repeats? Alright, questions? I can predict one of them. Number 5, yeah. So the integral from 2 to 7 of 2 times x plus 3 to the 1/3 is that? Dx. Okay. What would you do on this one? I actually neglected to do this yesterday, but I should have.
Substitute.
Substitution, right. Actually, yeah, you better substitute. If this were plain old 2x parentheses x plus 3, you'd just distribute and do it normally. But yeah, let's substitute. U equals x plus 3. What's du?
Dx.
Yeah, 1 dx or just dx. Is that line right over?
Yeah.
It is. Can somebody rewrite this thing for me?
2,
Yeah, and by the way, feel free to pull the 2 in front.
Oh, you.
Get out of the way. You don't have to.
do you,
You do the 1/3.
And then U to the 1/3
do
du. There's something else we have to change. Let me see what it is.
what
Oh,
was
we
it
got
just,
the 7 in there too.
The boundaries.
oh, man.
These are X values. Change them to U values.
Oh.
10 and 5.
Oh, dang.
Yeah, you use this. So if X is 2, plug it in, and then U is equal to 5. And then this should be 10. So instead of from 2 to 7, it'll be from 5 to 10. That'll make a big difference. Now, let's do the antiderivative. 2 times, it's gonna be, what's the new power?
4/3.
U to the 4/3, and then divide by 4/3. What is that really?
3/4.
3/4, good. So 3/4 U to the 4/3, from 5 to 10. Now again, if we're actually plugging in numbers, numbers to the 4/3 power is a real pain in the neck. You could. So if you had, I'm gonna pull this 3/4 out. That's like 6/4, so it'd be 3/2.
Mhm.
Theoretically, you could do this. 10 to the 4/3 minus 5 to the 4/3.
Yeah, that's what I did.
I will accept that for now.
Wait, that's what I did too.
Okay, if you have that, then you can breathe a sigh of relief. That is in fact correct.
Nice.
What they did, U to the 4/3, how many whole U's are in there?
1.
1. How much is left over?
1/3.
Yeah, what is that really?
Cube root of U.
U times the cube root of U. That's what they did. So if we actually did that, it would look like this. 3/2 times 10 cube root of 10 minus 5 cube root of 5. And then we can distribute that in if you want. This would be, actually that'd be kind of iffy. I wouldn't distribute that in, frankly. But, yeah, that's an alternate way of writing the same thing. Let me see what I did. Okay. Next.
Oh, number 6.
Number 6, okay. From 0 to 4 of 5, it's very similar to the other one. The 5 parentheses, I forget what it was.
Wait.
X minus 2, so there's no mistakes, by the way. So the 1/3 d x.
Wait, Mr. Cochran.
Yeah.
On the number 5,
Uh,
I didn't do the 10 and 5. I kept it at 7 and 2 and still got the same answer. It's kind of weird.
Oh, did you plug this back in for x?
Oh, yes.
Yeah.
Oh, that's fine.
If you do that, then you saved yourself.
Oh, wow.
Yeah.
That's the same.
So if you replace this with x plus 3 to the 4/3, and then restore these back in, yeah.
Oh.
If you change everything back to x's, then you can bring these back.
Oh.
Yeah. Otherwise, you'll have to keep the new boundaries.
Gotcha.
Yeah. Interesting. Righty.
X.
I'm gonna pull a 5 out in front. So it's gonna be 5 times the integral from 0 to 4 of, and I'm gonna do u equals x minus 2, and du is pretty boring, dx. And there it is. 5 times, oh, I better not do these boundaries. This is going to be u to the 1/3 du. The new boundaries are going to be from -2 to 2. Make sense? So now, 5, let's do the antiderivative. It's u to the 4/3 divided by 4/3. It's kind of identical to that one.
Yeah.
3/4 u to the 4/3 from -2 to 2. So I'm going to pull the 3/4 out. This is going to be 15 over 4 times, this is going to be u cube root of u from -2 to 2. Let's see what happens. So 15 over 4, I think I'm going to need a new marker in a second. This will be 2 cube root of 2 minus -2 cube root of -2. So what's up with that? Take a look here. Minus a negative is what?
Plus a positive.
Plus a positive, but can you take the cube root of a negative?
Yeah.
Yeah, for example, the square root, you can't take a square root of a negative without going imaginary. But for example, what's the cube root of negative 8?
-2?
Negative 2. And negative 2 times negative 2 times negative. So the cube root of a negative, is that positive or is it negative?
Negative.
It's negative. I'm going to be a little sneaky and pull the negative out front.
Oh,
So
wow.
it's 2 cube root of 2 minus 2 cube root of 2. Guess what that gives you?
Wait, where did your,
Zero.
This, it's kind of like, what's the cube root of negative 2? It's the same thing as the negative regular cube root of 2. It just means it's negative. So what happens here? It's 0. Yeah.
Okay.
And 0 times anything? 0. That's a horrible 0.
Mhm.
Does that make sense?
Oh, yeah. Yes.
Okay. Any questions on the second fundamental theorem problem? Again, if the conditions are met, then you can use the quick method. If you are nervous, if you're saying, I don't know if all the conditions are met, you can always do it the long way, which takes like 10 times longer. But you can do it. What are the conditions for second fundamental theorem? There are 3 of them, actually.
One of the top,
The top has to be
the X,
x or a function of x.
right?
What does the bottom have to, boundary have to be?
Constant.
A constant. Any constant you like, and it just disappears. It could be 5 trillion or negative pi. It doesn't matter. It just vaporizes. And the third thing is, it has to be the derivative of an integral. In other words, they're trying to cancel each other out. Make sense?
Mm-hmm.
Pretty much the only thing it does is swap variables, and that's it. Everybody good?
Mm-hmm.
Let me grab a new marker. We're probably going to see you in a few minutes, but you get the enjoyment of having us greet you virtually.
Yeah.
Take out your notes. Let's go on to one last thing here. Looking at page 54. Ew. Second fundamental theorem. Good. Yes. Page 343. Hold on a second. 1. 5. Yes. This is going to be a little on the intense side, but I think we can handle it. I'm going to give you a little bit of notes first.
Oh my gosh, look,
Forgot which one to use for this one.
look here.
No, that's probably- let's see. That looks new. Okay. I want to talk just one last thing. It's not in the stated topic on the homework sheet, but it's a topic in there. If you actually started doing the homework, you'd run into this pretty quickly. It's something called average value. And it's relatively easy to do once you know the trick. Example. Let's just say y is equal to x squared on the interval from 1 to 4. I'm going to do a quick graph of this. I'm also going to zoom out ridiculously here. You'll notice that the x and y scales are not the same. No, I'm not going to do single ones, that'd be crazy. This is 1, 2, 3, 4. So the heights on this are going to be 1, 4, 9, 16. So in other words, I really, really zoomed in on the x-axis. My question is, we now know how to do 2 things with this graph. We can find the tangent slope anywhere we want it. How? Yeah, right. You're right, yes, that's true. The first derivative, or single prime. Yeah. So if you take the first derivative of y equals x squared, that'll give you the formula for tangent slope. We can also get the area under the curve. How? Antiderivative, correct. Taking the integral or the antiderivative, same thing. I wanted to do something new. Little practice here. I'm going to change y to f of x, which by the way is perfectly legal. Y and f of x are interchangeable. These are going to be almost dumb looking practice. Let's see. What's f of 2?
4.
Oh, how do you get that so fast?
Plug in 2 for x.
Just plug it in. What's f of 3?
9.
Yeah. F of 1?
1.
And f of 4?
16.
16. Okay, so no stress there. Just plain old plug in and get it. What I would like to know, what's the average value of this function? And again, this function is limited. It's only a piece of a bigger function. Y equals x squared unlimited is a different function. That's a much, much bigger function. This one is just a little, like, microscopic piece of that. So what's the average value of this function?
Like 7.5.
That would be a logical guess. How do you get it?
Add them all up and divide by 4.
Add them all up and divide by 4. Let me show you what would happen if we actually did that. If you, like, take the first and last and add them up, which is close to what you got there, and then divide by 2, take the biggest and smallest, average them, you're basically pretending that's a straight line. Averages, a straight average has a tendency to make a straight line. If you add them all up, and then you'd have it a little bit, straight line a little bit lower. But the question is, what's the average value? You notice it bends. That's going to throw our average off. Do you think the average, the real average, is higher or lower than the add-up average? Just look at the graph. The add them up and divide uses this. It's basically saying kind of like what's the height halfway through.
Would it be higher?
Well, in other words, the real one. If I were to say, like, what's halfway between 1 and 4? Like 2.5.
Yeah.
Look at the two heights. Here's the average. Here's the real.
The real's lower.
The real one's lower. Yeah, not by much, but a little. And by the way, this is not going to be exactly the average. It's close. But, oh, math people who remember your probably 5th, 6th grade math, how do you get an average of a bunch of numbers?
You add them all up and divide by
Add them
4.
all up and divide by what?
The number of the...
However many, the number of numbers. That sounds awkward, but however many things
The
you
number
have.
of numbers.
Okay, the number of elements, they call it, to make it a little less funky. In this case, we're going to do the exact same thing, but the question is, how many values are there between 1 and 4?
Infinitely?
There are infinitely many. This is awkward. You're going to say, yeah, I'll take the average. I mean, it's one thing if we're in 5th or 6th grade and you say, blunk, 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 add those up and divide by 4. All of a sudden we're doing, and dividing by what?
Yeah.
Infinity? That's, you first. I'm not going to do that. But somebody, and I believe it was Sir Isaac Newton, possibly, what's his name? I'm blanking on his name. The other guy who invented calculus. And they were arguing with each other about who invented calculus first. Phooey. Sorry, whoever you are. I'll think of it in like 2 minutes from now. But anyway, one of the two guys probably came up with this. Here's how they do it. How do you add up an infinite number of numbers? It's high time, you know, I had finally clued you in on derivative is the tangent slope.
Mm-hmm.
Let me, just quick review. The first derivative of f of x, for example, is what we call the rate of change of f of x. It measures how fast f of x changes. And when you draw a graph of it, that happens to be slope. The slope of a graph is a measure of how fast it's changing. If the slope is 2, that means it's going up like 2 units per second. That's always been true. In calculus, we discovered that. The first derivative is the rate of change. That's true in story problems, in physics, in math, in everything. Well, the antiderivative of f of x. And this is one of the key words of the year. It's an accumulator. It's an accumulator. It basically adds up an infinite number
How long did they figure that out?
of slices. Well, when they first designed it, when they first designed antiderivative, one of its main purposes was to get the area under a curve. And you know all the Riemann sums are doing? Rectangle, 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 rectangle. What integral does, and it's today I get to tell you why. You know, how do you get better and better estimates for Riemann sums?
You get more and more slices.
More and more slices. Does that make sense? Because you have less and less wasted space. But there eventually comes a limit, like poor human being slobs that we are. If you try and have 5,280 slices, that gets really, really tiresome.
Probably should measure like 6.
A, because it'll take forever, and B, because the numbers are going to be horrid. Let's just say you have from 1 to 4. It's easy if you slice it in 3 slices, because each one is exactly 1 inch wide. If I slice this into 5,280 slices, how wide is each one? 3 divided by 5,280, which is not everybody's fun number. And the heights of each one are going to be a bit of a pain. The first height would be 1. The second height will be 1 plus 3 over 5,280. These are going to be really tedious really fast. Is there a way we can do this?
5,000 times.
Watch this. And actually, it's fairly easy to show you now that you know all these pieces. I just need to remind you of something a chapter and a half ago. If you have delta x, and you get really smaller and smaller and smaller, it gets teeny weeny weeny and approaches 0, what do you start calling it? As delta x approaches 0, but don't let it actually get to 0, but as it gets teeny weeny weeny weeny, we start calling it something other than delta x. And we've been using it a lot in here.
Not like a limit.
Dx.
Oh.
Dx is a teeny weeny weeny change in x. This, we discovered this when we were doing tangent slope. Regular slope is between 2 points. It's delta y over delta x. Tangent slope is dy over dx. It's a microscopic change in y over a microscopic change in x. So small we can't see it. It's practically 0. It's not 0 because dividing by it would be unhealthy. But my buttons on these seem messed up now. Well,
Oh,
it's
yeah.
my life. So why do I bring this up? Well, do you ever notice you take the antiderivative like from A to B of f of x dx? You ever wonder why this has to be here? We just seem to slap it on at the end just to prove that it was a derivative so that we can take an antiderivative, which is true. That's still true. Let me show you what you're actually doing. Here's a graph. I'm just making this up. This is a graph of f of x. And let's say this is A and this is B. I want to get the area under a curve. Suppose we have a teeny weeny 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 slice. Like, if I had a big chunk here, I would call this delta x, because it's a change in x. I mean, I'm sort of stealing that from first year algebra. But you see why I call it delta x? Because it moves in the x direction a little bit. It's how much x changed. This is teeny weeny 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 weeny. Guess what I would call it? Dx. And how do you get the height of anything?
Plug it in.
Plug it in. Now plug in what? Plug in an x and get out what? Y. And what's another name for y?
F of x.
This is the base. This is the height. You're multiplying these and getting the area of a rectangle. Base times height. And this adds them all up. Antiderivative, that big snaky S, it's sort of like it stands for sum. And everyone know where that symbol actually came from?
No.
It came from Old English. Has everybody seen a copy of the Declaration of Independence?
Yeah.
Ever see something like this? What does that say? Pursuit. The pursuit of happiness. They write internal S's like that. How come? I just think it's because they thought it looked cool and there was an extra woo flare in the middle of something. It does look pretty cool, you gotta admit. That's an S. It's an actual letter S. They use this for S, it's sum. S for sum. That means you're adding up. Like I multiply, here's one slice, here's another slice, here's another slice, another slice, another slice, another slice, another slice. They're microscopically thin, so we're calling the base dx, and every single height is going to be f of x, then f of the next x, f of the next x. This just means I'm adding up all the slices from A to B of the and this is just the area of a rectangle. Which is actually phenomenally clever. I never would have come up with this. But they did, thankfully, and we can use it. How do I know that an antiderivative is an accumulator? Because this is an antiderivative, and it's a sum. When you sum, you accumulate things. It's just a synonym. Does that make sense? So, why do we care? Well, in math, we sometimes have lots and lots of numbers to add. If I had 100 numbers to add, I would just add them up. If I have an infinite number of numbers to add up, I can't add them up. But this can. How many x's did you say were in between here?
Infinite.
Infinitely many. There's only one tool on earth we know of that will add up the infinite number of numbers from 1 to 4. This. That's what they're going to do. They're going to do this. Now, what did you say about averages? You add them all up and then what?
Divided by the number of numbers.
Divide the number of numbers. Now, I can't divide by infinity, but we can divide
By dx.
is how far we went. What's the distance here? Don't work too hard. It's actually very easy. 3. It's 4 minus 1. That will give us the average value of this function. Does that make sense? I'll give you a general formula. The average value of f of x on the interval from A to B is integral from A to B of f of x dx divided by b minus a. The b minus a is just how far you went. So we're going to divide by 3, which is awfully a lot easier than dividing by infinity. Much more satisfying answer. Let's get the answer on this thing. Let's see what we get. They erased the per foot. That looks like that. There was a sitcom once where somebody was trying to recite the Declaration of Independence, and they started pronouncing the S's like F's, and it was pretty funny. But anyway. Let's try it. I want to wanna take the antiderivative of x squared from 1 to 4 dx, and then divide by what? You tell me.
3.
Yeah, 3. 4 minus 1. Better known as 3. Somebody do the antiderivative for me.
1/3 x cubed.
Right. 1/3 x cubed from what to what?
Four. One.
From 1 to 4. All divided by 3. So I'm gonna pull the 1/3 out in front. So it's gonna be 1/3, and it's going to be, what do you plug in first?
Four.
The 4. So it's 4 cubed minus 1 cubed, all divided by 3. Let's do it.
Like 1/9.
Yeah, this is 1/3 divided by 3. You can simplify that to 1/9. What's 4 cubed? I mean,
4 cubed. It's 16 times 4,
16 times 4.
which is 40 plus 24,
Yep.
which is 64.
64. Minus what?
Minus 1.
Last time, check. What is that?
63.
63. What's 63 divided by 9? That comes out in
7.
7. You just found the average value of this function.
It's pretty close.
Okay. And by the way, it doesn't always come out quite that nice. It'd be like usually 65 over 9 or something like that. It's not gonna be horrible, it'll be a fraction. But, yeah. And I'm not always gonna promise that the antiderivative is gonna be pretty. You might have like, something times the cube root of something, who knows? But it's doable. And then you just divide by something. Does that make sense? Alrighty. Your assignment is, we are skipping 5L,
5. Oh, and then
and we're skipping 5, sorry, I take that back. Hold on. No, I don't take that back. We're skipping, let me see, 5K and 5L, I'm just running out of lead. Oh, no, I didn't. Skip 5K, skip 5L, because the worksheet covered both of those. We're jumping right to 5M as in Mary. Let me see which of these I want to give you. Number 1, I definitely, oh, okay, that's easy. Number 5, I will give you a hint in how to do number 5. Number 9, you should be able to do.
It's page 343.
Yes, correct, page 343. 11, yeah, that's fine. 17 should be fine. 19 should be, you won't like me, but that's okay.
Square root of 5.
Number 27.
Oh my god.
Yes, find an average value.
Look at this optic.
What I would like you to do, actually tell you what, skip number 5 for now. That actually takes a long time. I'm gonna do that in class tomorrow.
Okay. What are all the numbers you want us to do?
So 1, 9, 11,
1, 9, 11.
17, 19, 27.
Okay.
And skip number 5. This is homework number 5M on the sheet, but, and then skip number 5.
17, 19.
17, 19, and 27.
Is your problem?
Yes.
May I please get my book?
You may do. What is that?
Yep.
Okay, we go to it. You get about, you actually get about 20 minutes.
Oh,
Plus
well.
or minus. Anybody have to search today, or?
Nope.
Okay. You're all set then.
See you later, Ella. Set her up.
Yeah, go for it.